Assalamu alaikum. Z-score is a way of standardizing results, measurements, or data in relation to the bigger picture. This has several applications in biostatistics. We start with a real-life example. This is a tumor, a certain tumor, pleomorphic adenoma of the parotid, measuring 54 millimeters in diameter. How relatively big it is in relation to the bigger picture. These are the results of just one series of pleomorphic adenomas, my own, and it can show the spread of the sizes of the pleomorphic adenoma between a maximum of 59 here and a minimum of 16. It also shows the average size, which is about 32 millimeters, and gives an idea about how the values spread around the average size, because the standard deviation is 10 millimeters or so. So this 54 millimeters tumor should be somewhere here. It's obviously well above the average, but can we put a figure to the position rather than use descriptive terms like big or very big? The answer is the standardized indicator, the Z-score. And it uses this simple formula in which the Z-score can be obtained by finding the relation between the tumor and the average tumor and divide this by the standard deviation. So we get how far is the tumor from the average size in terms of numbers and fractions of numbers of standard deviations. So we need four pieces of information to obtain the Z-score. The formula has four pieces of information. Number one is the raw score itself, the 54 millimeters. Number two is the average tumor size, which is 32 millimeters something, and we divide this by the standard deviation, the 10 millimeters, and then we can obtain the Z-score. And this will give us an idea about its standardized position in the distribution. Z-scores are based on a fundamental concept of statistics, the area under the curve. If we have a distribution of certain results and that distribution can be categorized as a normal distribution, then we can make some safe assumptions. We can about the distribution of the data around the mean. The mean is in the central point in here, and one standard deviation away from the mean, either sides, would have 34% of the data. This would total up to 68% of the data would be within one standard deviation around the mean. Take this to two standard deviations, and then you would have more than 95% of the data within these two limits. And if you take it further to three standard deviations, you would obtain more than 99% of the data within three standard deviations from the mean of a normally distributed measurements. The parotid tumors in this particular series has a fairly normal distribution, not perfect, but fairly good. So we can apply some of these assumptions. We would know that within one standard deviations we would have 34% extra to the mean, and within two standard deviations we would have an added 13 point something percent. So we would need to obtain the position of the Z-score for the specified tumors in relation to the number of standard deviations and fractions of that number in order to give an idea about how big it is. The z-score can be obtained from the observation, which is 54 millimeters, minus the mean, 32 millimeters, divided by standard deviation. This will give us something just more than 2.1 z-scores. Because of the difference in the size between 54 and 32, there will be 2 standard deviations and a small fraction. So it should lie in here. So this would tell us that this tumor is very big. It's bigger than 95.4% of all the pleomorphic adenomas in this series. If we take another example, say a tumor of 23 millimeters, this is less than the value of the mean, which is 32.8. So the difference is about 10 millimeters. That's one standard deviation in this series. So we'd expect 23 millimeters to be somewhere in here. So it would be given one z-score because it is the distance between it and the mean is one standard deviation, but we'll give it a negative value to indicate that it is less rather than more than the mean. So what's the value of obtaining this standard score, the z-score? What does a z-score indicate? It indicates few things. We've been through 2 of them so far. It would indicate the number of standard deviations above or below the mean, and the fractions of this. So we know now that this 54 millimeters tumor is more than 2 standard deviations above the mean. We know its position within the distribution of the other tumors. We'd also get a probability of obtaining this. We know that it's more than 95% of other tumors, so it falls into this very small percentage outside the 95% of the other similar tumors. These are the first 2 values. But we can also know how significant is the difference between this tumor and other tumors in the distribution, because if it exceeds a certain limit, the p-value, we know that it would be significantly larger than others or significantly lower than other tumors of the same type and the same distribution. So it forms part of the basis for the p-value. It can also help in telling us whether 2 different distributions are similar or different in terms of the distance between their peaks divided by a pooled standard deviation. If they are very different, the differences between the peaks in terms of the pooled standard deviations will be significant or not. And it also contributes in the measurements of confidence intervals. This equation will come to it a bit later in this presentation. So this is just to re-emphasize how the z-score is obtained from a raw score, like a size of a certain tumor, for example. Knowing that a z-score is just another standard scale used in the measurements. You forget about the real values here and you use the other score. What you need to do from the values, the real values here, is to get how many standard deviations this real value is from the mean value. And once this is obtained, the same point corresponding to the other scale here would give the z-score, would give how far it is from the mean in terms of z-scores rather in terms of the real difference. Remember, there are 4 pieces of information in the equation: the raw score, the average score, and the distribution, and how the scores are distributed, the standard deviation, From these three figures, you can obtain the fourth, the z-score, and vice versa. We'll see how you could actually obtain x if you know the z-score, and vice versa. This is the second value of the z-scores. It helps in predicting the probability above a certain limit or above or below a certain cutoff point. Say we are dealing with another series here. This series of measurements have a mean of 68. So 68 will be here, and a standard deviation of 6. Each standard deviation will be about 6. What proportion consists of values greater than 80%? We would want to know, for example, how many students have marks above 80%, knowing that the average score was 68 and the standard deviation is 6. We transform this 80, this figure that we would want to get the probability, the percentile probability of it, into a z-score. 80 minus 68 equal 12, divided by 6 equal 2. So we know that the 80% mark is 2 standard deviations above the average score. What is the probability of a student getting a mark above this, above 80%? The probability is very low indeed, because we know that within 2 standard deviations from the mean, above and below, 95% of the marks would be somewhere here. So on the two sides, about 2.5% here and 2.5% on the other side. So we'd want to know the percentage on one side, above, not below the 2 standard deviations from the mean part. It should be about 2.5%, just less than 2.5%, above 2 standard deviations from the mean. That is the probability, because we set up the cutoff limit 2 standard deviations from the mean. And that's exactly how we find out whether a certain measurement or a certain result is significant or not significant. We set up the p-value, the level of significance, at equal to or less than 5%, which would mean that 95% in here are different from the test result or from the data obtained from a measurement. If we have this 5% cutoff point, 2.5% will be more and 2.5% would be less. Any value in this area will be significantly different from the vast majority of the other measurements in the same series. It would be significantly different. This is the basis of the p-value. And of course, you can set up this cutoff point at less or equal to 1 in 100. So then this will be almost 3 standard deviations above or below the mean. This would be the probability of having a measurement or a result more than 3 standard deviations away from the mean is even less than obtaining it in more than 2 standard deviations only. The chances here would be 1 in 100. The chances here would be less than 5%. Another application for the z-scores. Say another surgeon wants to do some parotid surgery and want to know how likely is it that he will get tumors of certain sizes, pleomorphic adenomas, if he is doing, say, something like 25 patients in a year, 2 patients per month or so. You want to use the figures obtained from my series in order to estimate the probability of the sizes of the tumor that he is going to encounter in his next 25 patients. And he wants this with a degree of certainty of 95%, like 19 out of every 20 operation he would want to expect the average size of the tumors he is going to take. Here, z-scores could also provide the answer, knowing that from the old series, the average score was 32 millimeters for the tumor size, and the standard deviation was about 10 millimeters. So the new surgeon wants to know the range of sizes of the tumors he is going to encounter in his next 25 cases, getting some insight from the old series. A 95% degree of certainty would translate into 95% area under the curve, that is two standard deviations above and 2 standard deviations below the mean, that is to say 2.1 z-scores above and below the mean. The mean of the old series was 3.2. Now, rather than using the standard deviation of the old series, we'll use the standard error, which is the standard deviation divided by the square root of the numbers of the patient in the new series. So this would be 10 divided by the square root of 25, which is 5. The standard error would be 2. So the mean for the tumor is 32 plus or minus z-score multiplied by the standard error. This is 36.2 millimeters as a maximum and 27.8 millimeters as a minimum. Because if you slot into this equation, 32 plus or minus z-score of 2.1 multiplied by a standard error of 2, that is plus or minus 4 point something, 4.2. So these will be the limits of the expected tumors 95% of the time. So this can be expressed as the degree of confidence is 95% because we have used 2 z-scores above and 2 z-scores below the mean. And this is exactly the basis for the concept of confidence intervals. The new surgeon wants to have a high degree of certainty that the tumors he is going to encounter would fall within a certain range. And we've calculated that range as plus or minus the average tumor size from the old series, the 32 millimeters plus or minus 4.2 millimeters. The 95% degree of certainty means that only 5% of the time, that is one operation in every 20 operation, the tumor size will not be within the range that we have calculated, would be either more or less than this. But in the remaining 19 operations, you would expect the tumor size to be within the range that we have calculated, and that is the confidence intervals concept. Z-scores are presented as positive if they are more than the mean and negative when they are less than the mean. This can be easily changed if we choose. You could mark out the middle point, the mean point, in a new scale with any chosen value, say 50 rather than 0 for the z-score scale. So if you have a new scale in which the middle point is 50, one z-score above the middle point would not be plus 1, it would be 50 plus the new standard deviation, which is 10, it will be 60, and one standard deviation below the mean would be 40 rather than -1. So just a way of making the figures all positive. If you have the middle point and the chosen middle point like 50 or 100, and then have all the points on the scale as positive integers. And of course, you can change the z-score to percentile calculations also fairly easily. We know that the mark of one z-score above the mean would mean the mark of 68%. Two z-scores above the mean would be the mark of 95%. Three z-scores would be the mark of 99.7%. The mark, for example, of 90% should be in between these two, and it is actually 1.2816 z-scores. So anything above this would be in the top percentile, the top 10%, any mark above this 1.28 z-score. A z-score of 0 would mean that the score is pretty average. It lies exactly in the middle. A z-score of -2.5, for example, would mean the chances of obtaining this would indeed be very low in here. So z-scores can be transferred to percentile calculations fairly easily from certain tables. And finally, a very similar way to the standardization of figures by z-score can be used to standardize difference between two separate groups in terms of their pooled standard deviation. Like if you have two separate groups of, say, tumors, pleomorphic adenomas done in two areas by two different surgeons with a certain average here and a certain average for the other group, you can standardize the difference between the two groups in terms of the effect size, or a Cohen's d, which has an equation very similar to the z-score. You find the difference between these 2 points in terms of the standard deviation. If the difference is very small, like less than 0.1, then there is very small difference between the two groups. If the difference is closer to 0.8 standard deviation, that is, the difference between the two peaks is about 1 standard deviation, then there is a large difference between the two groups and they are significantly different. By this, we come to the end on this presentation on the z-score and its applications in biostatistics. Assalamu alaikum.